Hello Science Alliance, alright my IGCSEs, I am Lara. I stream free live lessons into the internet and you are coming to the IGCSE physics ones, which is a good choice because I am actually trained to teach physics to A level. So I have less imposter syndrome in these ones than I do when I'm like teaching kids about the oceans or the woodlands. I'm in my comfort zone here, so hopefully you are too. Right, it's actually lesson 3 of our energy module, but you don't really need to have seen the other lessons. This is quite a nice little standalone lesson. I will catch you up. Hello Debbie in the comments. I'm going to try not to mention the comments too much because I know a lot of people watch this YouTube one so that they don't get distracted by the comments because the Facebook comment thread is quite... but I can see your comments and I do appreciate them, okay? I see you, even if I'm not actually going to talk to you or laugh at your jokes. Cool. Right, we'll sort of start the activity because it takes a little bit of time to get going while I'm recapping you on what we did last week. So if you've managed to find 4 spice jars that are the same, brilliant. If you haven't, just use 2, that's totally fine. I'm going to start by putting cold water into 2 of my spice jars and some food colouring as well. If you've only got 2 spice jars, then just put cold water into 1 of the spice jars. I don't know whether I should actually have an ice cube in there. That'd probably be fine. So yeah, if you're just doing 2 spice jars, obviously just fill 1 jar with cold water, but I'm going to do double everything, okay? So last week we've been talking about how energy gets transferred through things. So last week we were talking about conduction. We held a metal spoon and a wooden spoon and thought about why the metal spoon seems colder, even though, like, aren't they both the same temperature because they've been in the same room? You remember? And we worked out it's because basically the metal spoon is kind of stealing energy from your hand. So be really careful, IGCSE chums. We don't ever say that particles start to vibrate because all particles are always vibrating a little bit. But the particles in your hand are vibrating a lot. They've got a lot of energy because your body is warm, right? So when your body holds the metal spoon, the particles in your hand that are very warm, they vibrate into the metal spoon, the particles in the metal spoon, and those particles into the next particles along and the next particles along, and we've looked at how this means that heat ends up getting transferred along the spoon. And what you call it when solid particles sort of vibrate into each other, this kind of domino effect, it's called conduction with a duh, not convection, which is what we're talking about today. So I asked you, are liquids and gases good conductors? Do you remember last week? And you said, well, I mean, you didn't say anything, but I said, no, liquids and gases are not good conductors. And you can probably see why. What I'm doing is, by the way, very rudely off screen, terrible telly. I've got cold water into 2 spice jars now, and I'm going to dye the cold water blue. There we go. That's what I'm just going to be faffing around with while you're looking at this. So no, liquids and gases are not very good conductors. You can see why, because especially in a gas, the particles are really far apart. They're not really experiencing each other at all. They're not bonded together, so those vibrations are going to take ages to pass between the particles. And the same as a liquid. It's sort of a bit like a ball, the particle arrangement in a liquid. The particles are touching, but they're moving around constantly. The bonds are constantly breaking. So liquids and gases not as good at conducting. In fact, they're quite good insulators. But they are both fluids. Usually in sort of everyday life, we're used to just talking about liquid as being a fluid. If someone tells you to drink lots of fluids, they don't mean take in lots of air. But in physics, a gas and a liquid are both fluids because they both flow. So they are very good at doing convection, which is what we're talking about right now. I'm still dyeing this cold water blue, which is not a very scientific thing to do, to be honest, because when we do the astronomy module, which is coming up fairly soon, we'll do it this year, we will then actually, like, blue things, like blue stars are hotter than red stars. But anyway, I thought this is just going to help us to, it's a good quick reference point, isn't it? What else do I need to tell you before we do our activity? So liquids and gases are both fluids. I will also tell you that when liquids, well actually when solids or liquids or gases get warm, they expand. So the particles spread out. This is really important actually, I promise you. I'm not just chatting to fill time. because this food colouring is taking ages to go into the jars. No, this is important stuff that you need to know before we do the activity. This is going to give you a head start when I say, how did that happen, children? Why did that happen? So particles of anything. Well, let's say a gas, because it's easier to draw. God, these pens are terrible, sorry. Particles of stuff, when they get warm, they get more energy and they spread out. This is a horrible spoiler for our density lesson, which I really like, so I'm sorry about that. But if this was like a gas, you heat up the gas, then what happens is, why I'm feeling the need to draw this, the particles get more energy. So they spread out. Now this is important because actually there's a point in this lesson where I have made a kind of language mistake. It's important to note that when liquids or gases or solids do expand. They stay bonded together, but they do get ever so slightly bigger, like metal. When you heat it up, it does expand. Anyway, let's talk about a gas. It's important to say that when gases get warm, they expand, but it's not the particles that expand. So the atom, we'll talk about atoms later, but the like particle of oxygen, if you like, or whatever in the air, that doesn't change shape. It's just that the oxygen particles get more energy, so they spread out. So the air itself takes up more space. Is that okay? We'll talk about this more as we go along. Right, now I've also got some really, really hot water. Please don't get nearly boiling water and then hold it like above your laptop while sort of concentrating on other things, okay? Don't do that. That you must not do. But I'm going to do it right now. I'm filling my other 2 spice jars with very warm water. And then what we're going to do, and this isn't even the cool part of the activity, this is just something that we have to do, is we're going to get a little bit of cardboard which fits over the lid of the jar. And we're going to turn the jar upside down and the cardboard's going to stay there. But we don't even have time to talk about why today. We'll do pressure another time. But you need to cut a little bit of cardboard that fits over the jar. Not perfectly, you need it to easily cover the jar. Do you get what I mean? I've given you quite a lot to do, haven't I? So you need to cut out 2 bits of cardboard, if you haven't already, which are going to fit over 2 of the jars. Okay? I'll show you it on the screen. I've sort of done a little picture so that you can think about what's going to happen. Here we are. What is going to happen when we take the card away and why? While you're doing that, I'm going to get my red food colouring and put it into the hot water jars. Because you can see now, hopefully this is starting to make sense. So what we're going to do is, we'll do this activity twice. We'll get a jar of cold water and we'll balance it. It'll be fine, honestly, but this is why I said to bring a baking tray so it doesn't all spill everywhere. We'll get a jar of cold water and we'll balance it on top of a jar of hot water. And then we'll do the opposite. We'll get a jar of hot water and we'll balance it on top of a jar of cold water. What's going to happen when we take the card away in both those situations? And I've said, if you know, because some of you will have done this with me before. It's a really cool activity. We've done it a couple of times. If you know, can you think about what keywords you would be using to get actual marks at IGCSE? Because it's all very well, isn't it? Understanding something, but are you actually going to get a point? From a tired examiner who's already marked hundreds of these things, who's just looking out for a couple of words that they can tick and go, yes, point. What words are you going to use to get those points? I'm putting quite a lot of food colouring in because I think it'll be better if I do. But I'm nearly ready to go, actually. Someone in the comments is asking about the Lego story. The Lego story is tomorrow at 10:30 on YouTube. This lesson that I do is the IGCSE physics lesson. I mean, to be honest, like, they're not as different really as you might think. This is still really just a chat and an activity, which is what the Lego story is. There's just no story told with Lego at the end, I'm really sorry. So if you want a story told with Lego, you've got to come onto YouTube at 10:30 on Thursdays. How are you getting on? Have you come up with some ideas? Yeah, I gave you a big clue, didn't I, with the warm things spreading out. Okay, let's do this. Such a good activity. Okay, I've got my little bits of cardboard. I would encourage you to watch mine before you do it yourself and learn from my mistakes. If you've only got 2 jars, then don't do the first thing I do, do the second thing I do. Okay, so the first one we'll do is hot on top and cold on the bottom. So I'm going to do, no, hot on the bottom and cold on the top. The first one we're going to do is hot on the bottom. Hot bottom is the first thing we're going to do. If you've only got 2 jars, don't do hot bottom. Do cold bottom in a minute, okay? Clear as mud, wasn't it? What did I just say? I agree with Jenny B. Oh, I see. Good. You're cold water. Oh, all right. Nice. Yeah, right. I know. I'm not going to say the comments out loud because it's spoilers for the rest of you. Okay. Hot on the bottom, first of all. You can see that, can't you? You're close enough to get a good view of what's happening. Yeah. Hot on the bottom. How many times can I say that? So, if hot's on the bottom, we need to put a piece of cardboard. What could possibly go wrong? On top of this jar of cold water. Turn it upside down. Don't be a hero, okay? Don't have any fun. Just turn it upside down and put it on top of this jar, right? So, card on top of the cold water. Flip it upside downy. Let it go. It stays. Wow. Don't have fun. Stop having fun. Just get it on top of the jar because that's not the activity that we're doing today. And then, oh, hello, Izzy B. I thought it must be you. And then I'm going to pull the card away. Have you made a prediction? You thinking about what's going to happen? Good. Wow, what's happening? The two are mixing together. Wow, it's so beautiful. I haven't got a great view there, have you? I wonder if there's still time. Not really. Sorry. You missed it. You've got to do it yourself. I mean, you can see they're kind of still mixing together. So yeah, you're probably not surprised to find that they have mixed together. Instead of red and blue, we have purple. Someone on Facebook yesterday, I mean, the chances of you saying this are quite small. Someone explained that with the heat will be neutralised. So just a note that we're not talking about neutralising here. Neutralising in science is something to do with acids and bases, which we're not going to do in this physics course. So you wouldn't say the heat had been neutralised. You would say, well, I suppose the cold and the hot have mixed together. Let's move on, shall we? So I've got another bit of paper. That was hot on the bottom. Now we're going to do hot on the top, which is more fun to say. Hot on the top. So I need to put my card on top of my hot. And if you're only using 2 jars, then you do this one with me, okay? So cardboard on top of the hot jar. Turn it upside down. Let it go. Stop having fun. Stop. Just get it on there. Great. And then we're going to pull it away. I'm going to turn it around because I don't want to pull too much away. Okay, here we go. Izzy B, you've done this before, haven't you? Woo! There we go. Right, what's happening? Or what is not happening? Is that what you're expecting? It's good, isn't it? So we've got, I think actually what's happened is I've got some blobs of red food colouring that are very dense because they're solids, they're not liquids, so they have dropped down into the blue. But you can see there's a very big difference here. Flip you around. There we go, look. So this one is the hot on the, yeah, I think that is actual food colouring that's falling down more than the hot water. But you can see we've got a very clear distinction, haven't we, between the hot and the cold. Whereas on that one, we really haven't. Why not? Well, exactly right. And a horrible spoiler for the density lesson. Things that are less dense, things where the particles are further apart, it's what we call density. It's the same amount of particles, but it's just the material is spread out more, right? So hot water and cold water, the hot water is more dense because the particles are more spread out. Things that are less dense float, and things that are more dense sink. So basically what convection is stuff getting hot, so rising up because it becomes less dense. And then when it gets to the top, it's cooled down, so the particles move closer together again, so they become, no, careful, I was going to say the particles become more dense. That's not right, is it? The substance becomes more dense because the particles are closer together. So it sinks. At this point on Facebook, I turned my lava lamp on to demonstrate this beautifully, and then my lava lamp just went, yeah, you didn't turn me on early enough. But I turned my lava lamp on this morning, so you can see it. Lovely example of convection in action. Here we go. Look, lava lamp, wax, hot bit at the bottom. Wax gets hot, particles move apart, wax becomes less dense, wax goes up to the top. Wax is now not near the heater bit, so wax cools down, so particles become closer together. So wax becomes more dense. So wax sinks down. But then it sinks down, so it gets hot, so the particles spread out, so the wax becomes less dense, so the wax, you get it, don't you? Ah, oh, so relaxing. Yeah, so this is called a convection current. I've got another fun example of a convection current that I'll show you, which has to do with planet Earth. There's loads of convection currents around planet Earth. I'll tell you why it rains at the equator. Go on. I've got this lovely PowerPoint here. So the reason it rains around the equator is because here is some of the air around planet Earth. I'm not going to bother to do it all, but the sun and in that air are water particles. Okay, so in among the air particles around Earth are water vapor, drops of water. So the sun shines on Earth, pew 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 pew, and the middle of the Earth we haven't got time to talk about why, but it's the centre of the Earth that heats up more. So this means that the air particles around planet Earth, especially around the equator, around the centre, they get hot. You would think that it's the sun that heats up the air particles around Earth, by the way, but it's not. It's Earth that is heating up the air particles. So these air particles closer to the equator, they get hot. And when they get hot, what do? What happens when particles gain heat energy? They get more energy and they spread out, don't they? So the air becomes less dense. So it rises up, which carries the water particles with it. But then because they're far away now from Earth, they cool down again, and cold air happens to hold less water. You don't need to know that for your GCSE, and so it rains. And that is why you get rainforests. That's why it's really rainy at the equator. It's why it's hot and it's wet. Anyway, right, moving on, because this is the bit that's a convection current. Let's forget about the water. What happens to the air is sun shines on Earth, pew, 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 just like that. The air around the equator heats up the most, as we've discussed, so that those air particles spread out, so that air is less dense, so that air rises, but this leaves a gap, okay, and into this gap flows cold air. There we go. And into those gaps flows cold air, and into those gaps flows cold air, and at this point the warm air that has risen up is quite far away from Earth, so it's got cold, but the air that's next to the equator, that has got hot again, so that rises up, and that is what a convection current is. So the clouds and the air around Earth, there's loads of little convection currents all around Earth like that. Phew. Okay, definitely time for you to do some questions, isn't it? So I've got some, well, maybe I won't even pull you away from the screen. I think you can handle this. I've got you some questions. Oh, go on, I'll pull you away for just a sec. So what's nice about it is that quite often it's just a one-word answer that they want, or a short calculation, or sometimes just tick in a box. But occasionally you will get like a 3 or 4 or 5 mark question where they want you to write a bit. And it would be lovely, it'd be so nice if you got a long written question about convection in your exam, because there's just certain like points that you have to hit in order to get all the 5 marks. So this first question is to get you to put those points in order, but also to sort of help you get them into your head. The second question is to add a little bit more, and then the third question is an image, and I want you to pick out the examples of convection. All right, so question number 1, the kitten is cold. You got a room here with a radiator and some stuff, and then a kitten sitting far away from the radiator, which they pointed out on Facebook yesterday is very unrealistic, I'm sorry. But the kitten's very cold. You've got to put these stages in the correct order to heat her up before her eyes get frostbite. What did we do? So put these in order, please. I've put A, air particles gain energy. B, the radiator heats the air. C, cold air is pushed out of the way. D, then is heated by a radiator. E, and the cycle continues. F, so spread out. G, and sinks. H, and rise. Can you put those in order? And then if you've done that, if you're like, too easy, yeah, can you include the words denser and less dense? This is where I went wrong, actually. This is where I've done something that would definitely not get me a mark at IGCSE, so you're going to have to be really careful there. Add in some words denser and less dense to these steps somehow. The next one is, can you have a look at this little picture and see how many examples of convection you can see? So we've got someone with a hob, They've taken a pan off the hob and they're kind of flipping the food around. There's a window showing some clouds and some hills outside. There's some cupboards with some pans in, some spices. There's a tabletop, there's some salad on the table, there's salt and pepper. There's a pan on another hob in the foreground. And then the final question is a beautiful example of a GCSE question that was actually asked a few years ago. Don't know if you've ever seen this. Sometimes in tiny little spaces, I don't know, like maybe a caravan or band practice room or something, you get a little fridge which has a freezer inside it. And you will find, if you come across one of these little fridges, that the freezer bit is always at the top. Why inside a tiny little fridge is the freezer section always at the top? Margazata, I'm enjoying reading your comments. Oh, hello, is that Tamara? Well, you've got to be careful saying cold air rises, because cold air doesn't rise, does it? Does it? No, it's warm air that rises. All right, Andy. Oh, is that Casper? Hello. Cold autumn or dense, splendid. Yeah, seeing some good comments here. Hello, Ibrahim. Hi. Hello. Tara's there. Splendid. Right, toast. Right, elite. Right, Carrie. Oh, it's Carrie, sorry. Not Andy. Hi, Stanley. Oh, Margazata, I hope you're not too disappointed. So much enthusiasm for the Lego story from you. I hope I didn't... Oh, that's what you meant, tomorrow. Okay, yeah, I see what you mean, yeah. Oh, yes, just a typo, I get you. That's okay. Oh, good. It would be brilliant. If I had time, I'd just put Lego stories into everything. I suppose I should say, if you don't have like a Facebook account, if you're not signed in and you can't comment, but you would like to comment in this video, I have got a page, a post up on my Facebook page at the moment saying that I'm live. So if you've got a Facebook account and you go to the Theatre of Science Facebook page, then right at the top it'll say, comment here if you're watching live, and you can comment on that if you like. And I will say hello to you at the end. Because YouTube comments are a bit weird. It's like, I feel like on Facebook, if someone sort of who you didn't want to talk to tried to get in touch with you, then your adult would definitely know straight away. Whereas on YouTube, I feel like as an adult, I haven't got as much of a grip on YouTube. Like if someone tried to comment to my kid on YouTube, I wouldn't necessarily know about it. So yeah, totally understand if you're not commenting on YouTube and would rather put a post on Facebook. Okay, got an answer from Izzy B. Oh yeah, Izzy B, you have made the mistake that I made about the air particles. All right, Carrie, what have you put? Yes, that looks good to me. Yes. Gosh, it's tricky to put the letters to the... nearly. It's BAFHC, is it? Oh, I don't know. Should we go through it? Do you feel like you've had enough time? I'll be silent for a couple more seconds and then we'll go through it. Thanks for liking this video, by the way. Thanks for subscribing and liking. It is nice. Blade, you don't think question 1 makes any sense? All right, well, that's a good reason to go through them. See if we can make it make some sense. Okay, right. Well, the radiator heats the air. Okay, there's hot water inside the radiator. In fact, so the radiator gets hot and it heats the air. So the air particles gain energy because that's what happens when stuff gets hot. That's literally what being hot is the air particles moving around more. So the radiator heats the air particles gain energy, and what happens when air particles gain energy? They spread out. Air particles gain energy, so they spread out. So what's next? And rise. So because they've spread out, they're less dense, so they're now going to rise up through the other air, which is colder. The radiator heats the air particles gain energy, so they spread out and rise. Okay, so you've got air that is going up. Then it's heated by the radiator and the circuit. Oh, cold air is pushed out of the way. So you've got cold air at the top, but now warm air is rising into that cold air. So the cold air is pushed out of the way and sinks because it's now more dense than the air around it, right? It's going to sink. And then it gets heated up by the radiator and the cycle continues. Now, this is where I made a terrible, embarrassing mistake. Can you add the words denser and less dense? I've put very quickly just typed in becoming less dense, but that's not what's happening, is it? Air particles gain energy, so spread out, becoming less dense. No, it's not the air particles that are becoming less dense. The air particles are staying exactly the same size and density. It's the air that is less dense. I can't believe we're learning about this before we learn about density. If you're confused, it's because I haven't taught you about density. I'm really sorry. We'll learn about density quite soon. But anyway, the air becomes less dense. And then next one is okay. Cold air is pushed out of the way and sinks because it is denser than the warm air. That's okay. Kitten is pleased. Is that all right? This is obviously saved on YouTube now, so I'm going to move on. You don't have to mark it right this second if you're confused. To be honest, if you Google convection current steps IGCSE physics, you'll come up with loads of great examples as to how to get marks. So I'm going to move on. How many examples of convection can you see below? Name and explain them. Did you get the air outside? So we've talked about how the air around Earth, so clouds are warm water particles which have risen and then cooled, so that air is taking part in that convection current. This is a hot pan. Hotter than the air around it, so the pan would be heating air, which would be rising, and then cold air would be falling around the pan. I put Earth. Inside Earth is one big convection current, you know, like the mantle, like all the liquid rock down inside the Earth. That was a bit tenuous, maybe. This pan is certainly convection. Be rubbish if when you put soup on a hob, the very bottom got hot and the top stayed cold. So what happens is the soup at the bottom gains energy, so the particles spread out more, so the soup gets less dense, so it rises to the top, so the cold soup sinks, and that's how soup heats up. It's good, isn't it? And well done if you spotted that this person is also hotter than the environment. So the air around this person's body is going to be heating up. So it is going to be rising, and then it's going to be cooling, so it's going to be falling. So that would be a tenuous convection current as well. Oh, this was such a beautiful past paper question. Say what you like about exams, but I think this is really smart. They knew that you would spend ages and ages researching convection, and you knew that particles get heated up, and so they spread out, so the stuff becomes less dense, and so it rises, and then it cools down, so it sinks. You were all ready to talk about that. And then they went, okay, so there's some cold particles up high. Talk about that. How confusing, and what a beautiful way of checking whether you'd actually understood. So, the freezer is at the top of the fridge. So the air at the top of the fridge is coldest, yeah? And what does that mean if the air at the top of the fridge is cold? It means that the particles are close together, so that air is the most dense. And what happens when dense stuff is above stuff that's less dense? It sinks, doesn't it? So the coolest air is at the top of the fridge. This is denser than the air below it, so the cold air sinks. So the warmer water, the air at the bottom, gets displaced, it gets knocked out of the way, and it rises because it's less dense than the air surrounding it. And so as it gets to the top, it gets cooled by the freezer, so it becomes more dense, so it sinks. It's good, isn't it? That was a really nice way of checking whether you'd understood or whether you were just trying to remember what you'd been taught. So cool. Right, we're nearly at the end. I have got just to tie in, because there's 3 different ways that heat can be transferred that we talk about. Conduction in the solids, like the sort of domino effect that we talked about last week. Convection, which happens in fluids, liquids and gases, that we talked about this week. And radiation that we're talking about next week. So I've got you a couple of really nice practice paper questions where it's just like writing one word answer or ticking a box. See how you get on with these. Question 1. Energy is transferred from this hot mug of tea to the surroundings. Complete the sentences below using the word conduction or convection. So energy is transferred through the sides of the mug by, is it conduction or convection? In the air around the mug, energy is transferred by conduction or convection. Question number 2. The picture shows ice cubes used to heat some hot coffee. Adults are weird, aren't they? So you got ice on the top, hot coffee on the bottom. How is the coffee at the bottom of the glass being cooled? Is it A, conduction, B, convection, or C, condensation? Question 3 is a bit weird. You've got to read the question carefully. You've got a hot object and then a gap and then a cold object. The gap between these hot and cold objects can be filled with air, iron, a vacuum, no particles at all, or water, which will allow thermal energy to pass between the surfaces the fastest. A, air, B, iron, C, vacuum, or D, water. You've got until the time it takes me to write the answers on the board, and then we'll go for it. Question 3 is so weirdly tricksy. Okay, are you ready to go through it? So you've got a solid mug where the hot tea is cooling down. So energy is being transferred to the surroundings. Energy is transferred through the sides of the mug by conduction, because conduction, it's a solid. The mug is solid, so the particles of the mug are vibrating into each other until they knock into the particles of air. I suppose you could have thought, well, the energy's been passed on to air, so maybe that's convection, but no, that was heat travelling through a solid and eventually knocking into the air particles on the other side. So that was conduction. And how the air around the mug was having energy transferred to it, that was convection. So yeah, the mug is heating up the air and the air particles are getting warm and rising and then cooling down, so falling, and then that's continuing again and again. So the first one was conduction and the second one was convection. This one, again, it's a fluid, isn't it? It's a liquid. So it is the coffee at the bottom of the glass is being cooled by convection this time. This water or liquid, this coffee is cooling down, so becoming more dense, so sinking, and so this warmer coffee is rising. So it was convection. And the last one was iron. I thought that was quite tricky because it's sort of, the diagram suggested that you were looking for an insulator, but it's asking which one will allow thermal energy to pass between the surfaces the fastest. So it was the solid, where the particles were closest together, so that conduction could happen. So yeah, it was iron. It was a bit weird, that one. All right, I've just got 3 questions for you because I just want to know how much I've taught you, basically, and these are things that might get picked up on an exam very quickly. What do you remember? We talked about electrons last week. We talked about how, well, I won't spoil it. What is it about the electrons in a metal that make metal such a good conductor? Is it A, they're very small, B, they're free to move around, or is it C, they have a lot of energy? If you didn't come to last week's lesson, you don't know this, but you are about to learn it. So metals in particular are very good conductors, partly because their particles are very close together if they're a solid, so the heat is passed along, the vibrations are passed along, but it's also because metals have got these electrons in it. And what is it about the electrons that makes metals such a good conductor? It's because they're free to move around. They're literally called free electrons, so they whiz around and transfer energy a lot faster. Number 2 of 3, what word describes materials that aren't good conductors? If some materials are not good conductors, what are they? Are they A, insulators, B, insulation, or C, convection? The answer is, if something isn't a conductor, it's an insulator, so it's A. Insulation is made out of insulators, but strictly speaking, the opposite of conductors is insulators. And finally, hopefully I've taught you this today, what gets less dense when air heats up? What gets less dense when air heats up? Is it A, the air, B, the molecules, or C, the atoms? Again, without doing a whole, I love my density lesson. We do a little activity where I get you to see if you can sink a Lego brick in water. It's fun. But this is not that lesson, so apologies that we're using the word density already. What gets less dense when air heats up is the air. The air becomes less dense. The atoms on the molecules stay exactly the same size and density, but they just move further up. That's really unfair to tell you that without actually telling you what density is, so don't worry too much if you got that one wrong. Right, that is the end of the lesson. Thank you so much for joining me. Thank you. I love these. I love all the lessons that I do, but I do feel like the camaraderie on this one is particularly awesome. It's nice to be kind of working towards something, right? Like even if you're not actually ever thinking that you will take a physics IGCSE, it's just nice to have kind of like a little goal. Okay, I'm going over to my Facebook page to see if anyone's left me a comment on Facebook, because like I say, you don't always want to or can't always comment on YouTube. So I'm going to, this is how long it takes me to go to my Facebook page, because I've only been doing this for 5 years and I'm very old. View profile, there we go. Right. Thank you so much for liking and subscribing and all that stuff. I'll do my ad just in case there's anyone here who is new, who's not come across data science before. So how this business model works is, I just accidentally fell into it in lockdown. I started streaming free lessons sort of for the glory and the likes, and then home educators wanted me to keep going. So I set up this, well, I didn't set it up. There's a very lovely website called Coffee. You can set up a coffee page where people can send you money. So I set up a coffee page and said, if you send me £5 a month, that'll be enough for me to keep going. And it is, and you are, so I do. And it's literally a full-time job. It's so weird. Like, I am trained to teach physics up to A level, and I don't do any private tuition. I don't do any small Zoom classes. This is literally my full-time job. Like, if you are watching this now, you are my student. So yeah, if you go to my about section on YouTube, or you could click the sign up button on Facebook. Hopefully I've put the sign up button in a lot of different places. I think it's in the comments of this video. Then you get a coffee, send me £5 a month, and yeah, that is literally how anyone in my family makes money now. It's so weird and so cool. Could not have planned it this way. Oh, I've got some comments. Hey, Bean and Bud, that freezer one was tricky. Yeah, it was, right? I know, it really was. I mean, that's why we do the tricky ones. Oh, hello, Tamara. Oh, Sandrine, that is, it's a cat on a radiator. Nice, look what you did there. There's Matilda and Elwood, hello. We've had a whole science day, you have, hello. And really, like, you've done about 15 lives with me now, right? Because of all the stickiness this morning. Jacob, hello. Freya and Hannah, hello. I've said you all your names totally out of order. There's Kai as well. And there's Willow and Darcy and Jackson. Oh, this is nice, isn't it? All the regulars. The Core Science Alliance crew. There's Rocklin as well, hiya. Completely said you all out of order. But I think I've said hi to all of you. Sandrine, with Little Kitten, and Tamara. And there's Matilda and Elwood. You've got a reply. Who's replying to you? Oh, put pictures of your fossils on another post. Oh, okay, thank you. I will have a look at that. There's Izzy B. Splendid. All right. I forgot to get to the end of my advert. I'll send you nice stuff basically if you sign up. You send me £5 a month. You're very much paying for the lessons and the free printouts that come with the lessons. But I do send you nice things to say thank you so much. It's the best job ever. Thank you. So if you sign up to support me with £5 a month, you receive I always call them rainbow glasses, but because you're doing IGCSE, I'll call them diffraction glasses because that is what they are. They split white light into all the colours of the rainbow so you can see rainbows. They're amazing. And I'll send you a description of how they work. And I'll send you Favourite Science Magazine, which is ever so good, which is why it takes me forever to bring it out. I'm writing another one as we speak, but it just takes so long. But if you sign up now, I'll send you a past issue. Moulds, this one has got a free home compostable plastic bag with it. You build a tray, you put some food in it, you grow some different colour moulds, you identify them. It's got Choose Your Own Adventure. It's got a comic about how penicillin was discovered. Do not be deceived, IGCSEers. I know it all looks all like kiddie and comic-y, but there's actually loads of information in there. Took me ages to research that. Same with this one actually. If you sign up with £6 a month, which you are very welcome to do, obviously, you get this issue about time, which again, there's quite a lot of physics in this one. It comes with a sundial you can make. It comes with an activity to try and explain how Einstein's theory of relativity works. It comes with a lovely comic about a woman who used to sell time fairly recently, and about how like time zones work and all that stuff. And if you sign up with £9 a month, which again you can support me with like £100 a month if you want, then I'll send you a third magazine. But yeah, mainly the reason you're paying me is like for all the teaching and the planning that I do, which is very much appreciated. I mean, it's not appreciated. It's like, this is how I earn money. This is my job. So thank you for paying me for my job. Brilliant. Right. I think we've had some more comments, so I'll just have a look at those. And then I better go. Or is it, I think it's just Radiator Cat actually getting lots of comments. Oh, it's Sasha and Amelie. Hello, Sasha and Amelie. I'm never sure like whether I should say people's names. Come on. All the comments. Oh, yes! Sasha and Amelie are all about the little pictures of the kittens today. That is very cute. There's Willow and Darcy and Jackson again. All right, you three. There's Izzy B again. There's Tamara. There's the cat on the radiator. Splendid. All right, I've said hello to everyone. So I will go, and I will see some of you tomorrow for my free all ages lesson about evolution in the oceans, or for my Lego show about conkers. Or I'll see you next week for where we learn about radiation. Now, we're doing quite a dangerous activity next week. You really need someone else with you if you're doing next week's activity. But it was so good, it worked so well. Even my husband was sort of pleased with it and wanted to take part in it. And he's a bit over all this now, that it's worth doing. But yeah, if you can have someone else with you next week, it would help. We're getting a food can, not a drinks can, with the lid off, like an empty one. And we're filling it with very nearly boiling water. It's not advisable. But I'm going to do it anyway. Right, I'll see you all very soon. Thanks for joining me. Bye. Oh, bye, Carrie. Good to see you. Bye, all the fun, Mike. Bye-bye. All right, bye, Debbie. Bye, Rocklin.